Okay, so let's see. Do we have what we want? Okay. So we've been through the first part. Of these exercises, right? So yeah, so there are a couple of questions here, right? Can you actually learn about actions we're not taking? Well, we know we don't, because it's obvious here that whenever we take some action with 0, then we can estimate it as 0, and when we don't take it, then you cannot estimate it anymore, right? So one thing we can do is, as the next part of the exercise says, well, we can do it later actually. Now let's say that we have an optimal policy that we want to estimate for the data we actually have. Okay. Now this is an important aspect of this. So let's use this one, right? So here we can estimate the utility of this policy. Okay, so how to. So this one we don't want to do it anymore. Let's forget about it. Right. Okay. We don't really need to plot this right now. So that's right. Estimated parameters. Estimated policy, and finally we also have the utility of our policy, right? Okay, so this is what we get, right? Maybe we can just let's save theta here, just to know what it is. Okay, and just print it. I cannot see anything. Sorry, that's my fault here. Okay. So now we want to do as before. We are estimating theta and the model, and the policy, and also the utility. Okay. So now we are trying to estimate parameters theta, and policy is well, 0.1, we know it already. And what else? Do we have something else? No, that's not. So the parameters are these ones, and our estimates are these ones. They're pretty close. Okay, even though we don't really take one action so often as the other one. Okay, our estimate of the policy is pretty good as well. Okay, right. So now if we want to find the utility of some other policy, yeah, what would that utility be? So one question is, how do we estimate the utility of some other policy time? Okay. Method 1, use importance sampling, right? How does this work? Well, we said that the expectation of some function in the utility is basically the integral or the sum of u of x, p of x, and you can rewrite this as q of x divided by p of x times p of x. So now the idea is that p of x over q of x there and q of x here, and this one you approximate by sampling. Okay. Right. Approximate by this. Okay. So this is sum over possible x's, while here we are summing over samples xt. And xt is coming from okay. From Q, sorry. Right. Okay, so when we estimate this under some distribution P, I will only have samples from Q, then we can do it like this. So we can use the same idea for estimating the value of the policy. That is different from the one I've actually observed, right? So now the only thing you have to add here is the probability of taking an action now, right? Under one policy versus the probability of taking the same action under the other policy. Yeah. So we have already the data. Okay. So let's say we have alt pi is equal to 1, 0. Okay. Fine. Now we want to the same, go through all this, okay? We know the 80s, we know the whiteys. Let's say, what is this alt hat u going to be? So, yt more or less times the probability with which you are actually taking the action divided by the probability that the other policy will take the action. Okay. So you also have to go over the number of actions. Let's see how many actions we have. Yeah, 2. Okay. percent just to make it easier. Okay. Right. Okay. And then I'll have you should just divide by the number of samples, right? And then let's see how this compares. Okay, so this is one specific policy. We can do it for some other policy. Where's our okay, so this seems to be correct as far as I can tell. If we take the actual same, no, that's not right. So that's correct. Yeah. There's nothing. Why is it complaining now? I don't know. That's weird. Let's see why this is coming up here. Okay, I'm using floats to index my array. Why is it float? It's definitely a random choice, right? So it should be a number. You can see what's the problem here. T is a number. Oh, it's hot theta is wrong here. Hot pi. Okay, but still don't know what. Where does it complain? It complains for the T? I don't understand why it complains. It's only here. Doesn't complain for this. And for this. Why is this not an indicator? Okay. Fine, let's just do it like this. Okay. Right. So there's another problem here. Why is it complaining now? Why is it not in the I don't get it. I just don't understand something. I guess I understand kind of. Can I make an array? No. Another I. It is not NP. Oh. Okay, it can be any type you like, right? Okay, the type equal int. Okay, the type int. That's what now? Okay. Fine, okay. After all this, that is one. Right, so now we have these parameters, these estimated parameters, and this estimated policy. Okay, and we see that whenever we take this action, we will take the value of 0.17, and we take action 1, we'll take an expected value of 0.94. So we should be taking this action more than that action. But the policy that we actually have selected initially takes mostly that action, so it has a higher expected, has a low expected utility, around 0.24. And the policy that we evaluate here takes mostly, well, it takes always the first action, right? Yeah, so there's an obvious optimal policy here. Yeah? So just write this. What's the obvious optimal policy? Let's see, what's this one? Okay. So what is the obvious optimal policy here? We have expected utility at time t given at at is equal to a, right? Is equal to sum, okay, well, integral actually, the utility of y, and then the probability of y given at equal a, and if we know the parameter theta, okay, then this is the utility is y as well. So y dp theta y given at equal a. So that's the expected value of y given at equal a. And that's basically just, if we know the parameter, and that's basically theta a, right? So max expected value of utility for action equal to a is the same, is the maximum over theta A. Okay. So now the idea is replace theta hat or theta with theta hat and choose A in argmax theta hat A, right? Okay, so that's the basic idea. So how do we do this? It's not very difficult. Let's say there isn't an argmax, I think. And the argmax, yeah. Okay, so this works. Then we write alt pi argmax, okay, of 0 of hat theta equal to 1. Yeah, that seems to work. Okay, so let's just run the whole thing. Yeah, sorry. Okay. So now we have a policy that is different from before. Okay. Let us bring a new policy. And it should give us a better utility. Okay. Now, think about what happens when you have less data or when you have more actions. So let's say you have only 10 samples, okay, or 100 samples, so not so few. Okay, so it was. There will be some cases where you get a worse result. Sometimes, it's not very often. Not very often at all. It depends on variance of the thing. So here our variance is just 1. Yeah, so let's make the variance be higher. Okay. Well, I'm surprised. The estimated parameters are 1 and 2, fine. So as long as our estimates are pretty good, then it works pretty well. The only problem will arise whenever we have not so many samples. So our improved policy will not be very good. But most of the time it seems to be working here. Well, the differences are quite large, so. Just make it slightly cheating here. Right. So, I mean, it depends on how many samples you have and how far away the two different means are. but here is an example where the actual parameters, the actual mean is higher for the first and the second one, but the estimate is the other way around. Okay. So now this is interesting because here the estimated utility, okay, so this is not the real utility, but this is our estimate of the utility. So our estimated utility tells us that our second, our new policy should be better than the other one. But that's basically because our estimated parameters are wrong, in the sense that the theta for one policy is higher than, well, theta 2 is higher than theta 1 in our estimate, while it's the other way around for the two parameters. Yeah. So so this is the code. Now, if you wanted, you could estimate a better policy. But estimating a better policy usually requires just actually using a model. But if you want, you can use the model parameters instead, right? So all the actions, right? Then you can estimate the utility of action 1. So hat u 0, alt hat u 0 as well. Now you can estimate here, well, probability of taking the action, right? So it's like hat I A, and then this is the expected utility. So the expected utility for policy, right, is like what we have here, right? Okay, so this is what we use. And the only thing we care about is sum over all the actions of the probability under the policy of taking the action. Okay, and then the rest is basically theta A. So now we replace this with an expectation, with an estimated expectation. So let's put this a hat there if you like, or some other model of the parameter for distribution. So now we just need to calculate this. It's not very difficult. We have already got hat theta. Okay, and we also have the alternative policy. Yeah, and I guess that's it. And then we can print those things. And have the same result, basically, right? Just because in this very simple model, the only thing we are doing for the theta is counting. Yeah, we're not doing anything else. You know, if you had a more complicated model here, and you're using, let's say, a normal estimate, a normal prior, and a Bayesian estimate of the theta, then you get slightly different results. So these numbers will be different. But if you're just using this very simple model, then these results are the same. Okay. All right. Let's see. Now there is a question there in the exercise, says if we know theta, right, then the best thing to do is just to take the action that maximizes the utility under that theta, right? And that means always taking the same action, never changing. There is no need to be random or anything. But what will happen if you don't know theta? Yeah, that's the question. Wouldn't you need to change actions, or do you need to? Can you always keep the same action? I mean, the answer is obviously you have to change actions. You just have, let's say, 10 samples, then the first 10 samples can tell you something wrong. Yeah. So here this is action 0 is better than action 1, but it seems from my estimates that action 1 is better, so it's the other way around. So your pulse is not very good, even though your actual utility is maybe actually I should also plot the utility of the for the real thing. Yeah, so it's kind of very different. Okay. We only have a small number of samples, of course, so that's part of the reason why it's so different. Now, what else? Yeah, the parameters can sometimes be none. There's nothing kind about that. So the last thing is working with data. Okay. So I have a slightly different model here. Here we have a model with covariates. Now the mean is a matrix, and we have a covariate, let's say data and action, and have another distribution here. And then this can be 2 by 2, I guess. And this would be like the covariate model. Now we can have a covariate policy, or let's call it a Markov policy. So it only depends on the x. Okay, that is already there, so x can be none. So now it has 2 parameters, okay, and number of actions is 2. But now the path we select depends on the observation. Now we can do the same analysis more or less, but we have the added complication that we have to generate the axis as well, right? So I guess I will leave it for you to try and extend to this. Okay. Let's say that this one also generates the covariates. And let's say they have equal probability, maybe. Okay. Now if we just briefly go through the remainder of this exercise, what I'm supposed to be doing. So for this exercise you can try and just simulate data from the model that we have already. So here we already generated data, so we can generate more data and see how well the policy behaves. Okay, but then these estimates should be the same ones as what you get by using the true model parameters. Now, more generally, we can do the same thing for covariates. Just have more parameters to estimate. It doesn't make any difference. And probably the outcome policy should also depend on what the x is, and not just be independent of x. Now, estimating a good policy generally requires that you estimate some model for the policy, for the outcomes, given the actions on the axis, and this is enough for you to be able to find the optimal action. Yeah. In some cases, you don't want to do that. You want to do if you don't use a model explicitly, then you can always use something else, like gradient descent or something like that. But as long as you always have a probability for taking actions, right? So as long as you have the probability for A and X, you should be able to find the maximizing action, the one that maximizes expected utility. You can get expected utility given the action and the X. Okay? And the policy that is optimized is the policy that maximizes this for every possible X. So it defines a mapping basically from X to A that maximizes expected utility according to some estimate of the distribution. The only tricky part is getting the estimate of the distribution, and for this you need to make sure that you disentangle the effect of the policy through which you got the data, that's called pi 0, from the model parameters. If you don't disentangle them, then you have a problem because your estimates will be biased. But in these simple examples, we saw that it's not difficult to disentangle them in general. We just have to be aware that the data has been collected with some policy and not just obtained naturally, let's say. Okay, so P star A given X is equal to, let's put here. So then the optimal, okay, is going to be 1 if the expected utility of A given X is greater or equal than the expected utility of A prime given X for any other A prime. Okay? That's the basic idea for this. So you don't really have to define completely what the policy is. You just have to be able, for any possible method you observe, to find the maximizing action. Okay. There are some cases where you need to define the complete policy. That's cases where this is restricted to be in a simple form, like a linear function or something. But we haven't covered that. We haven't done any gradient descent or anything like that in detail. So if somebody wants to do it, they are free to do it, but you're not obliged. So if you have any more questions, because tomorrow I have another engagement at noon, and Sumaya is still going to be out of commission, then we'll just have to use the Piazza platform. But you should be able to use the ideas that we did here. Here we did them today with just very simple models, but you can use the same ideas for any arbitrary complicated model, if you like. So instead of just finding one parameter, it could be a more complicated relation between X and Y, or between A and X, or anything like that. Okay? Okay, if you have nothing more, then I will stop now, and we can take it over on Piazza later.